topic of today's video will be generating function and recurrence relation for Bessel functions, right? As we studied in our last video, that Bessel function is noted by jpx, right, or j minus px, and that can be generated with the help of some function, a kind of exponential function. We will see that. First I will start with the generating function. So it states that generating function for Bessel function is actually the coefficient of t to the power n, and that is e to the power x by 2 t minus 1 by t, right? And here the range starts from n equal to minus infinity to infinity. It means that the coefficient of t to the power n in this series is equal to the coefficient of t to the power n in the right hand side, right? Or you can say that, or coefficient of t to the power n in the expansion of e to the power x by 2 t minus 1 by t is equal to j p x, right? So this fact can be stated in this way also. So we'll start a proof of this thing. So starting with this function e to the power x by 2t minus x by 2t, it can be written in this way also, multiplying this x by 2 with the inner terms. So we'll get e to the power xt by 2 multiplied by e to the power minus of x by 2t. So you have exponential functions, right? And expanding them, you will get, first for it, 1 plus xt by 2 plus xt, and I should write 1 factorial over 1 like this, right? And second term will be xt by 2 whole square by 2 factorial, and so on. Nth term will be xt by 2 whole to the power n by n factorial, and the next term will be xt by 2 n plus 1 divided by n plus 1 factorial, and so on. So this is the expansion of this exponential function. And similarly for this one, we have this multiplied, these two series are multiplied together. That will be 1 minus x t by 2 to the power 1 by 1 factorial plus xt by 2 to the power 2 over 2 factorial, and then writing its nth term, right? Or should I write the pth term, because I need jp, so I should write the coefficient of t to the power p, that is a small change, and here I should write the pth term, p factorial, like this. This is minus 1 to the power p, and xt by 2 p over p factorial, right? And next term will be minus 1 to the power p plus 1 xt by 2 to the power p plus 1 divided by p plus 1 factorial, and so on, right? Okay, now these are two series multiplied together, right? So these are in product, and you have to find the coefficient of t to the power p. So at this point you can see that there are so many terms which will contain x to the power or 2t to the power p. As you can see that if this term is multiplied with this term, I have to make some arrows I think here, this term is multiplied with the first term, then you will get a term containing t to the power p, right? This multiplied with this. Similarly, if you multiply these two terms, you will get, oh sorry, I have written t in the numerator, however it was in the denominator, x by 2t, right? T, right? Now it is correct. And if you multiply these two terms, you will get t to the power p, because here you have t to the power p plus 1, and this is t in the denominator, so ultimately that will be t to the power p. And similarly for the next term that will contain xt by 2 to the power p plus 2, that should be multiplied with this term to get the required power of t, right? So writing coefficient of t to the power p, so coefficients of t to the power p in this expansion, e to the power x by 2 t minus 1 by t, and those are the first coefficient will be the coefficient of these two terms when you have their product, that will be x by 2 to the power p, yeah, divided by p factorial, right? And now see the second term, when this is multiplied with this, so you will get the coefficient of t to the power p as minus x by 2 to the power how much, p plus 1, yeah, p plus 1, or it should be p plus 2, because here you already have x by 2 1 power, so that will be added to this thing, so that will become p plus 2. Be careful at this point. And in the denominator you will have 1 factorial and p plus 1 factorial, right? I have to write one more term also, and the other term will be the next term will be x divided by p plus 2, and that should be multiplied with this term, and that will give me p plus 4, yeah, x by 2 to the power p plus 4, and from here you will have this 2 factorial here, and in that denominator that will be p plus 1, p plus 2 factorial. So you need 2 or 3 terms, right? So these are the coefficient of t to the power p, and it is itself an infinite series, right? And you can see that you can write this series in summation form, right? So trying to write this series in summation form by just watching its third or second term. If you watch this third term, and you can see that x by 2 is everywhere, right? And this is p plus 0, this is p plus 2, this is p plus 4. So I should write x plus 2p, I think. No, sorry, p plus 2n, p plus 2n, and n is starting from 0 to infinity, if I'm not wrong. Yes, right. And the sign is also fluctuating, and that will depend on minus 1 to the power n, right? Similarly, you have 2 into 1, that will 1 factorial, 2 into 2, that is 2 factorial, so that here will have n factorial and a p plus n factorial. So this is a generalized term, right? Okay, and you can see that what is this? This is jpx, right? This is jpx, jpx, right? It indicates that the coefficient of t to the power p in this expansion is jpx, right? And similarly, you can prove that also. Coefficient of t to the power minus p in e to the power x by 2 t minus 1 by t. If you try to find the coefficient of t to the power minus p, then you have to multiply. You can see that if you have to multiply these two, I have to remove these arrows. Okay, you have to multiply this term with this term in order to get t to the power minus p, right? And this term should be multiplied with this term, right? I should write it from here like this in order to get t to the power minus p, right? So I will write terms. So first you have to multiply this with this, so the coefficient will be minus 1 to the power p and x by 2 to the power p divided by how much? P factorial, right? And in the second term, this multiplied with this, you will get, yeah, plus minus 1 to the power how much? P plus 1 and x by 2 to the power p plus 1 is here, 1 is there, so p plus 2, and yeah, divided by p plus 1 factorial, 1 factorial, 1 factorial, p plus 1 factorial, right? Writing one more term, you have to multiply this third term with this next term containing the power p plus 2, right? So that will be plus minus 1 to the power p plus 2 x by 2 and that will contain p plus 4. Yeah, be careful at this point, because the next term will be x by 2t p to p plus 2, and here you have 2, so powers will be added, that will become p plus 4, right? And in the denominator you will have 2 factorial and p plus 2 factorial, and so on. And from this series it looks very similar to this series. First thing is that except that you have to take this common. Minus 1 to the power p should be taken common in order to get this series, right? So I will write minus 1 to the power p is taken common, and inside bracket you will have x by 2 to the power p over p factorial plus or minus, yeah, because minus 1 to the power p has been taken common, so minus and x by 2 to the power how much, p plus 2 divided by 1 factorial, p plus 1 factorial, plus x by 2 to the power p plus 4 divided by 2 factorial, p plus 2 factorial, and so on, right? Now you can see that this series is identical to this one, right? So it is JPX actually. So write it as minus 1 to the power p JPX, right? So you can see that, say that coefficient of t to the power minus p is equal to this much, right? And we know that when p is an integer, we did that in our last video. In case when p is an integer, then the two solutions are dependent. Means JPX is dependent on j minus px, and they are connected by a relationship, and that was j of minus px is equal to minus 1 to the power p times jpx, right? We have derived that relation in the last video. So I will replace this by j of minus px, but that replacement is only possible if we consider that p is an integer. So I have to mention that. So if p is an integer, then this is that, yeah, coefficient of that thing, then this answer is, right, or I should write it this way, is equal to j of minus p x if and only if p is an integer, right? So this replacement is possible if and only if you consider p is an integer. So that's why we can call this exponential function as a generating function of this Bessel's function. It means that when we expand this function, which is actually the product of two series, right, then the terms of this series are actually the Bessel's function. It means that the first term will be j naught x, second will be j1x, then third term will be j2x, coefficients, right? It means that if I multiply these two series and try to find the coefficient of x to the power 0, am I right? Yeah, t to the power 0, sorry, t to the power 0 on multiplication of these two series, then the coefficient of t to the power 0 will be j naught x. Similarly, the coefficient of t to the power 1 will be j1x, and so on, right? So here's a small proof of that, and now I will move to this recurrence relations. Similar to those legendary recurrence relation, we have Bessel's recurrence relation, right? And you know that why we call it recurrence relation. A recurrence relation is nothing but it is a relationship between the terms of a discrete numeric function, right? And we also call it a difference equation. Recurrence relation is also called as difference equation. Okay, so yeah, to start with, we have actually 6 recurrence relations, right? And the first 2 are fundamentals, and the later 4 can be derived from the first 2, right? So you have to remember at least the first 2 recurrence relations, right? So starting with the recurrence relations, right? The first is d by dx of x to the power p jp x is equal to x to the power p j of p minus 1x, right? This is the first recurrence relation and we have to prove it. Okay, and to prove this I have to use that jpx, the original formula of jpx. Where is that? Jpx, I have to use that jpx. This is jpx. I will be using this formula, and we'll try to evaluate the left hand side, right? So proof. since jp x is equal to how much? This one, summation n equal to 0 to infinity minus 1 to the power n x by 2 p plus 2n divided by n factorial p plus n whole factorial, right? So this is jpx. You have to remember this formula, and you can see the left hand side we have x to the power p in the multiplication of jp. So multiplying this with x to the power p, you will get summation n equal to 0. That x to the power p will go here, and that will be added to this power. So that will become minus 1 to the power n x by 2 to the power 2p plus 2n, right? And here you will have n factorial and p plus n whole factorial. So this is the result after multiplication with x to the power p, and you can see that we have to derivate it with respect to x. So I will be going to derivate this thing, differentiate with respect to x. So when you differentiate this left hand side will become d by dx of x to the power p jp x equal to differentiation of this thing with respect to x. Note that this is a constant, this is also constant, this is also constant. The term containing x is this much, and differentiating this term only. So we'll get summation n equal to 0 to infinity minus 1 to the power n, and this power will come here 2p plus 2n, and you will get to how much? X to the power 2p plus 2n minus 1, and I think this 2 in the denominator should be taken out immediately, and that is 2 to the power 2p plus 2n, if I am not wrong. Yeah, correct. And these two terms, yeah, this is the differentiation of this thing, right, with respect to x. And now I have to do this thing x to the power p. Okay, so if I write, where is that? If we can take this 2 common, you can see that, right? And this 2 will appear here, 2p plus 2n minus 1. Summation n equal to 0 to infinity minus 1 to the power n, and you can see that if you take 2 common, you will be left with p plus n, and that p plus n will be cancelled with this factorial function. You will have p plus n minus 1 in the denominator, so I am writing that directly. So x to the power 2p plus 2n minus 1, and that 2 is taken here, so you will write it as 2 to the power 2p plus 2n minus 1. You can see that both have same powers, x and 2, and I will write that in one bracket, and this will be n factorial, and this will be p plus n minus 1 factorial. So this is the differentiation, right? I hope we are correct, right? And now you can write these two in just one bracket. Okay, so it will become summation n equal to 0 to infinity, and yeah, x by 2 whole to the power 2p plus 2 minus 1, and where should be that? This is p plus n minus 1, and I have that p minus 1. Okay, this is p minus 1, so it should be p minus 1. Okay, yeah, I have to do some manipulation. And what about this 2? 2 to the power x by 2 will go there, and x to the power p can be written outside. But what about this? I think I made an error here at this point. It was not 2, yeah, it was 2p plus 2n, but not for 2. Yeah, it was x to the power 2p plus 2n, because when we multiplied with x to the power p, then it became x to the power 2p plus 2n, but this 2 was here 2 to the power p plus 2n, so it was a small error, p plus 2n and p plus 2n. Now it is correct, right? Okay, now you can see that you have x to the power 2p plus 2n minus 1, and you have 2 to the power p plus. You want that these x and 2 are in same bracket, so that they should have same power, but this x to the power 2p is here, so you have to split this p plus p. This 2p should be written as p plus p, and then x to the power p can be taken out here, right? In order to achieve your goal, you want that these x and 2 have the same power. The idea is that, so that you will be able to write in term of jp, right? So now you can see that I have taken this x to the power p outside, and inside we will be left with minus 1 to the power n, and now these have they both have same powers. We write it as x by 2 and p minus 1 plus 2n. Watch very carefully. I am writing this way, right? And divided by, this is n factorial, and it was actually p plus n factorial, but now it is p minus 1 plus n whole factorial, right? How should write this way? Bracket. Okay. Now you can see that this is clearly jp minus 1. Why jp minus 1? Because in the exponent you can see that x by 2 whole to the power p minus 1 plus 2n. Originally it is p plus 2n for jp. So if you have p minus 1 here, p minus 1, then you should have jp minus 1. This is the idea, right? We will replace it by j of p minus 1, right? So this is a proof for this first recurrence relation, and similarly we have another recurrence relation. The second recurrence relation is very similar. It is d by dx of x to the power p, x to the power minus p, jp x equal to minus of x to the power minus p, j of p plus 1 x. So this relationship is similar to that one, right? Except the fact that we have to multiply with x to the power minus p this time. So I will be writing a proof exactly similar to that one. So multiplying with x to the power minus p, starting with that proof. So this is your jpx summation n equal to 0 to infinity minus 1 to the power n x by 2, and you have 2p plus n here, yeah, p plus 2n divided by n factorial, and you have n plus p whole factorial, right? So this is a jp, and this time you have to multiply with x to the power minus p, and then you have to differentiate it. So I am doing those steps in one step only. So multiplying with x to the power minus p and differentiating with respect to x, right? So you will get the left hand side d by dx of x to the power minus p is multiplied with it, right? And since I am doing it in one step only, so I have to be careful at this point. Okay, summation n equal to 0 to infinity minus 1 to the power n, and this will become x to the power, you have multiplied with x to minus p, so that will become x to the power 2n. Okay, and this 2 should be taken out very carefully like this way, p plus 2n and 2n factorial n plus p factorial. However, I have not differentiated it yet, so I will write d by dx here like this one, right? So now I will differentiate it. So on differentiating it, I will get summation n equal to 0 to infinity minus 1 to the power n, and you can see that this 2n will appear here, and you will have x to the power 2n minus 1, and the denominator you will be having, okay, 2 to the power how much, 2n plus p n factorial n plus p whole factorial. This is the result after differentiation, right? And you can see that this 2 has power 1, so that will be subtracted with this thing, and this n factorial, they can be cancelled one term, that it will be n minus 1 factorial. So keeping in mind all of these facts, but be careful at this point, there is a danger, because in this step you are cancelling n, right? In that recurrence relation you haven't cancelled n, you cancelled that p plus n, and the index, the variable used for index is n. So when you cancel this index n is your index, be careful at this point. So there is a danger at this point. I will leave it question mark, and this is infinity and minus 1 to the power n, and this 2 will go here, so that will become 2 to the power how much, 2n plus p minus 1, but this n will be cancelled, you will be left with n minus 1 factorial, and this is a danger point. Now you have n minus 1 factorial, right? And since you have n minus 1 factorial, first I will complete it, and here you will have what, x to the power 2n minus 1, yeah, okay, yeah. So since you have n minus 1 factorial, you don't have n factorial here, so you cannot start with 0, right? because if you put 0 here, then it will become minus 1 factorial, and that is equal to minus infinity, right? It has no meaning. Or you can say that this will go to 0. 1 upon minus 1 minus infinity will go to 0, right? So there is no harm actually writing n equal to 0, but you should write n equal to 1, because that term will ultimately go to 0. So you should write this n equal to 1, right? This is an important point. When you cancel an index which is used for the range of summation, you have to change this range also, lower range especially, because upper range is infinity. Okay, now what I will do, I have to put jp plus 1, right? Okay, so jp plus 1 means x to the power, and you can see that you have x to the power minus p here, but there is no hope of getting x to the power minus p. You need this thing, and there is no hope of getting x to the power minus p. So I will multiply with x to the power minus p and divide with x to the power minus p, or you can say that I will do this, x to the power minus p multiplied and x to the power p multiplied, so that they will balance each other, right? And you can say that this x to the power p will be added to this thing, so ultimately it will become 2n minus 1 plus p, right? So I will add that x to the power 2n plus p minus 1. I think it looks good now. And here you have minus 1 to the power how much, and divided by 2 to the power 2n plus p minus 1, and you have n minus 1 factorial and n plus p factorial, right? The good thing is that the both powers of x and 2 are same. This is very necessary basic condition if you want the summation to replace by jp or j minus p, whatever. So they have same powers. That is a good thing, but the bad thing is that usually summation starts from n equal to 0, and you have to stick with this thing, right? Always try to convert the lower range of summation from 0, not 1. So I have to do some modification here. If I bring this one on the left hand side, then it will become n minus 1 equal to 0. So I will assume that n minus 1 equal to k, so that my new range will become 0 to infinity, right? This step we have done in the last video also. So what I will do, I will replace that index n minus 1 by new index k in order to achieve 0 in the lower range, right? So it will be converted to equal to I should write in bracket, right? X to the power minus p, yeah, and summation it will become k equal to 0 to infinity, because you are replacing n minus 1 by k, and here also minus 1 to the power how much, k plus 1, k plus 1, and here you will have x by 2, since they both have same power. I have merged them, right? 2n plus p plus 1, and in place of n you are putting k plus 1, so 2 times of k plus 1 plus p minus 1, so that will become 2k plus p plus 1, yeah, 2k plus p plus 1 divided by n minus 1. N minus 1 is replaced by k, so k factorial, and this is here, but n should be by k plus 1, so that will become n plus p plus 1 factorial. So ultimately you reached here, right? And now there is good chance to replace this by jp or jp plus 1, whatever. But you can see that this is minus 1 to the power k into minus 1, so that minus 1 will appear here, and ultimately we will achieve our target. So taking the negative sign outside, this minus 1 to the power 1 will be left with summation k equal to 0 to infinity minus 1 to the power k and x by 2, 2k plus p plus 1 divided by k factorial n plus, oh, not n, I think that was k. I replaced n by k plus 1, so that became k. K plus p plus 1 whole factorial, right? So this is what you got after replacement, and now you can see that this is nothing but it is jp plus 1, j of p plus 1, right? And since this index is immaterial because you can write k equal to 0, t equal to 0, n equal to 0. That is immaterial because this is actually an infinite series. K will not be there. When you expand it, no term will be containing k because k will be replaced by its value 0, 1, 2, 3 and so on, right? So that is immaterial. So if you compare this with this JPX, you will find that in place of p you have p plus 1. Everything is same, right? So you will write it as minus x to the power minus p j of p plus 1 x, right? So proved, right? So these are the two recurrence relations, right? And these two recurrence relations are called fundamental, right? And by the manipulation we can derive other relations also, right? You have to remember these two relations, right? Now I will try to find the third recurrence relation, and that is nothing. You have to just differentiate this thing on the left hand side and that's it, right? So third recurrence relation, right? I don't remember that relation actually. I remember only two relations, and from these two I can derive number of relations. And what I will do, I will expand this using that. What is that? First, this one, using the first recurrence relation, that is d by dx x to the power p jp x equal to x to the power p j of p minus 1 x, right? So you just apply the product rule, you will get differentiate this, you will get xp jp dash x, differentiation of jp will be jp dash, right? And since you are applying product rule, so jp x and the differentiation of this will be p times x to the power p minus 1 equal to x to the power p j of p minus 1 x, right? And what do I need? I need to divide it by x to the power p, and I will obtain a new recurrence relation. So jp dash x, and it will become plus p by x, am I right? Yes, j p x equal to how much? J of p minus 1x. So this is another recurrence relation, right? I will box it, right? So this is just obtained from that first recurrence relation. Similarly, from this one, second one, I have to differentiate it using d by dx of x to the power minus p j of px equal to negative of minus x to the power p minus p and j of p plus 1 x, right? And when you differentiate this, you will get x to the power minus p j of p dash x, and differentiation of this thing minus p x to the power minus p minus 1, right? And jpx equal to minus x to the power minus p j of p plus 1 x, right? And then dividing by x to the power minus p, you will get j p dash x minus p upon x, yes, j p x equal to minus of j of p plus 1 x. This is the fourth recurrence relation, right? And now the fifth and sixth relation, they are very easy. If you add them, you will get fifth recurrence relation. Fifth, add recurrence relations third and fourth. Third and fourth, you just add them, and when you add them, these two terms will be cancelled out. So we will get j p dash x plus, what is that? That's same. Both terms are same. Yeah. So twice it will become twice. So twice of jp dash x, right? Equal to addition of these two terms, j of p minus 1x minus j of p plus 1 x. So this is a new recurrence relation, fifth. And sixth, you can also subtract them. Subtract fourth from third. You just subtract them, this minus this, that this term will be cancelled on subtraction, and this will be added, that will become twice of this thing. So 2p by x, and that will become jpx, and here you will have, I think I have made an error here when I, okay, now correct, plus j p minus 1 plus j of p plus 1 x. This is another recurrence relation. So you have 6 recurrence relations, and first 2 are fundamentals and the other are just manipulations. Okay, so now, yeah, further we can use these those recurrence relations. Yeah, first and second, we can integrate these 2 relations also to get some new relations, right, involving integral operator. Okay, now I will add remarks. If I write the first recurrence relation, not the first one, well, that, yeah, first one, and try to integrate it. Okay, since from the first recurrence relation was d by dx of x to the power p j of px, and that became x to the power p j of p minus 1 x. If I integrate it with respect to x, right, so that this operator will be cancelled out, the integral operator, as they are inverse of each other, and here you will have integration. So ultimately, before this you have this integral operator x to the power p j of p minus 1 dx, like this, equal to, and this will be x to the power p j p x plus c. So it is a new result, right? Okay, and similarly from that second one, this is your first remark, or I should write it A, remark number A. From second, d by dx of x to the power minus p j of p x equal to minus x to the power minus p j of p plus 1 x, right? If you integrate it, you will get a similar result. Integration before this thing, and that is x to the power minus p j of p plus 1 x dx. And why should I bring this negative here, minus, that will become x to the power minus p jp x plus c, where c is the constant of integration, right? You know it very well. So you have 2 new results, and further you can always substitute in those first and second recurrence relation p equal to 0, 1, 2. I will do that. That will be my third remark number C. If you write again from first, that is d by dx of x to the power p j of px equal to how much? X to the power p j of p minus 1 x, right? If you put p equal to 0 here, put p equal to 0. If you put p equal to 0, you get, see, d by dx of x to the power 0 is 1, and this will become j naught x equal to x to the power 0 is 1, and this will become j of minus 1 x, right? But since p is 0, 0 is an integer, and in case of integer, you know that those jp and j minus p are related, or they are dependent on each other, right? And we can replace j of minus p by minus 1 times minus 1 to the power p times jp, and same thing can happen here. Since it is a negative suffix, so you will replace it by minus 1 to the power this much, this number, sorry, p is 0, and j 1 x. So ultimately that will become j1 x, and I will write this relation. I have used this relation, j of minus p x equal to minus 1 to the power p jpx, if and only if p belongs to an integer, right? So for p equal to 0, we have this is a differentiation of j naught x is equal to j1 x, right? It's kind of new result, right? And if you put p equal to 1, so putting p equal to 1 will give you d by dx of x j1 x equal to, here you will have x j naught x. So it is a new relation, right? So you can obtain a number of relations by just putting p equal to 0, 1, 2, 3 and so on. You can give any integer value to it, right? And now I will move to another class of Bessel's function, which has where p is, this p, where is that p where this P is especially of the nature of m plus half, right? Means in fraction form with a 2 in the denominator, right? So we'll be deriving those Bessel's function, and they have practical importance also in mathematical physics. So Bessel's function of the form J m plus half x, right, where m is an integer, right? So we are going to find the Bessel's function of this type, J of m plus half, right? And this time we have to again go back to the original point where we started, that is the Bessel's differential equation. And I have to add the differential equation, and we'll try to solve it not by the Frobenius series method as we have been doing in these videos, but by standard methods of solving a second order differential equation that you studied in your last semester course, right? You know that when you have a differential equation of second order and they have variable coefficients, generally you write a standard differential equation of second order as y double dash plus px times y dash plus qx times y equal to 0, where px and qx are functions of x. So you have several methods of solving them. The first one was method of variation of parameter, and one was the changing the independent variable. One was the removal of first derivative, you call it normal form also. So there are 2 or 3 methods, right, fundamental methods in order to solve that, right? So that the idea was that the differential equation with the variable coefficient must be converted into a differential equation with constant coefficient, or at least those kind of coefficients which can be solved, right? So the idea was that, right? So I will be using the same idea, but that idea works only for this case when this P is equal to m plus half, right? So recalling some of the facts from those theory of differential equations you studied in last semester, I will try to write in short those ideas, and then I will go to this, right? First I will write the fundamentals of solving a second order differential equation, which is particularly using this method, right? So that is that's kind of prerequisite to understand this thing, right? So you have second order differential equation for differential equation of this type, y double dash plus px y dash plus qx y equal to 0. You have differential equation of this type where px and qx are functions of x, they are not constants, right? Okay, then this differential equation I will calling it one equation, right? One can be put in equivalent form, and that equivalent form is like this. I should write it in u double dash plus, if I write here q, this is I should write small q x u equal to 0, right? So this is what we need. We need that this differential equation of this nature should be converted into this one. And what is the speciality in this equation? That you don't have the coefficient of u dash. We don't want that the first derivative is present, so that the solving it will become very easy, right? So I will let it equation number 2. We want that this is converted into this, but to achieve this goal we have to do some substitution, and that is done by this of the equation from this where what is u, where y is replaced by ux multiplied with vx. Obviously this u is a function of x, right? Okay. And this is this, and this vx is given by this formula. I have to write the formula, e to the minus half integration capital px dx, and this small qx is given by this formula, q minus p square by 4 minus half d by dx of px, right? So this is the kind of result you have to remember from last semester. However, we have a proof for this, how we obtained this, right? The idea is that we want that this complicated differential equation gets converted into the simplest differential equation with some particular value of qx. It's not like that you can solve this differential equation any time, every time. When qx is a constant, you can solve it by writing its auxiliary equation and then complementary function and so on. And when this qx is of the form of constant upon x square, I will write that qx equal to this much must be of the form some constant upon x square, right? So the idea is that when you get this small qx in this form, this constant can be 0 also, right, or constant upon x square or constant, right? So when you get this small qx in these two forms, we have a good hope to solve this second differential equation, and ultimately we'll find the solution of first differential equation, right? So the idea is that to convert a complicated differential equation of a type 1 gets converted into simplest differential equation of type 2, provided this qx comes out to be this form. Either it will be a constant or constant upon x square, right? And then the final solution is of this type: u is equal to ux multiplied with vx, where vx is given by this beautiful formula, right? And ux will be obtained from here on solving this differential equation. This second differential equation will give u, and v will be obtained by this formula. From multiplying u and v, you will get the final solution of the original differential equation, right? So the proof of this whole thing, or this whole method, is in second semester course, and the proof goes like that. I will tell that. You start with this thing. Let us make a substitution that y is equal to u times v, right? And then you plug this value here and here, here and here after derivating it twice, and then you collect the coefficient of u double dash, u dash and u, right? You want a differential equation in u, right? So when you plug this value here, you will be getting a differential equation like this: u double dash plus capital A times u dash plus capital B times u equal to 0, right? And then what do you want? You want that the first derivative should be absent. So you will pick up the coefficient of u dash, that will be capital A in my case. Originally that is very complicated, right? And when you put that equal to 0 and try to solve it, you get this thing: vx equal to this much, right? I think that was u dash v plus v dash u, if I remember it correctly. The coefficient of u dash was something involving v dash and v dash v minus something like that, right? And when you integrate it, you get this thing, right? And now your differential equation will be u double dash, and since you have chosen that the coefficient of u dash as 0, so you will be getting u double dash plus bu equal to 0, and that b is given by this formula, right? I'm saying it b, but that was this qx, right? And when you get this qx in this form, either it is a constant. When it is a constant, you just put that constant here, and that will be automatically solved, because you will be able to write the auxiliary equation for that case. And when you get this constant upon x square, there is again a hope to solve this, because when you have this term as constant upon x square, you should multiply the whole equation by x square, and that gets converted into a Cauchy-Euler homogeneous equation, right? You remember that the Cauchy-Euler homogeneous equation has the coefficient x square with u double dash, and the coefficient x with u dash, and with u no term, right? Constant term. So in both of these cases, the equation is solvable. But if you get any term different from these two terms, then you will be not to apply this method. This method completely fails. So the success of this method depends on the values of qx. Either it should be a constant or constant divided by x square, not x cube, only x square, right? So this is the idea, and now using this idea, I'll be trying to solve my Bessel's equation, which we solved by a Frobenius series solution, right? So we hope that we'll be able to solve it, right, by this method. So let us start. So Bessel's differential equation is, you should remember it, that is x square y double dash plus xy dash plus x square minus p square times y equal to 0. This is a Bessel's differential equation, and you know that this p is a non-negative constant, right? Okay, and yes, if I try to solve this differential equation by this method, then I should just use the formula. We have the formula here, right? Let y is equal to ux into vx be its solution. We hope that the solution of this equation is of this type, right? And when you plug this value here, and on simplification by equating the derivative of u dash to 0, I get this thing. So I will write that, where Vx is given by this formula, what is that, e to the power minus half integration, is that px dx. What is px? Px is the coefficient of y dash, and in your case your px is 1 over x, right? So I write 1 over x dx. You should note that your px is 1 over x, right? And when you integrate it, you will get log x, and minus 1 by root x will be the final value. On integration you can solve it, 1 upon root x. So this is your Vx by using this direct formula. And now using this, I will find this Qx first, and we'll see that what happens, right? Okay. And this small Qx equal to this much, capital Qx. Now what is your capital Qx? Your capital Qx is this much, this upon x square. This is your capital Px divided by x square, right? You should write it first in standard form, or I should replace it by here. When I divide by x square, I will be having 1 upon x here, right? And here I will be having 1 minus 1 upon p square x square, right? Now it is fine. That is in standard form, right? And now Qx will be capital Qx, that is this much, 1 over x, minus p square by 4. Sorry, I made a mistake. My Qx was this thing, 1 minus p square over x square. This was my Qx, minus p square by 4, the square of this thing, 1 by 4x square, and minus half differentiation of p, and differentiation of this thing will be minus 1 upon x square, right? And ultimately this will become 1 minus, I think these will be minus 1 by 4 and plus 1 by 2, so ultimately that will be plus 1 by 4, right? So plus 1 by 4 and 1 minus p square over x square plus 1 by 4 x square. Yeah, so this is the Qx. But now the question comes, whether this method will succeed in solving this Bessel's differential equation. At this point, that is complete failure. But because you can see this term is not a constant, obviously, and this is of not this form, constant divided by x square. If you put p is equal to 0, imagine that if you put p is equal to 0, you will get 1 plus 1 by 4x square. That is not either a constant or not of this type, right? But if you put p equal to 1 by 2, you see it, you put p equal to 1 by 2, these two terms will cancel each other, right? That will be 1 by 4x square, that will cancel. So putting p equal to 1 by 2 is giving some hope that this method of previous semester can be applied to solving this Bessel's differential equation, right? We want that we should use this method for some particular value, not for all values of p, but at least there exists a value of p, so that this small qx comes out to be a constant and this method is applicable. So I choose small p equal to 1 by 2, right? So that is working here. So I will write that if a small p equal to 1 by 2, then our desire of getting this qx as a constant is fulfilled, right? This qx is equal to 1, and now I will use this qx here, where in this formula, where is that differential equation, this one, right? And I will solve that. Then the transformed differential equation u double dash plus qx will be 1, u equal to 0. This will be your differential equation from this, right? Differential equation of the second, and you can solve it, write it auxiliary equation, that will be m square plus 1 equal to 0, and you will get m equal to plus minus eta as its roots. So auxiliary equation, that is m square plus 1 equal to 0, or it will give m equal to plus minus eta, and since we are having complex roots, so the complementary function, or that will be a solution, because the right hand side is 0, there is no particular solution, only complementary function will be there, and that will be the general solution. So the solution of this differential equation, right, I should write it as equation number 1, right? Therefore the solution of 1, and that is in u, so ux is equal to c1 cos x plus c2 sin x, right? You write the solution in this form, This is the solution of this differential equation, right? But we are seeking the solution of this differential equation, Bessel's differential equation. We are interested in the solution of Bessel's differential equation, and that was y is equal to u times v, and we have found u, we have found v, and we have to multiply it, right? Therefore y is equal to, I will write that, ux into vx, and that will be, what is vx? 1 by root x. So 1 by root x times c1 sin x plus c2 cos x. So this is the solution of Bessel's differential equation for p equal to half. Note that we have made a choice that p equal to half. This is not the complete solution. Complete for p equal to half, not for all p, is solution if p equal to how much? Half, right? Okay, and now what I will do, should I compare it with that standard solution we obtained in our last video, that was y is equal to c1 times jpx plus c2 times j minus px, in case when p is a non-integer, because again here p is a non-integer. So we should compare with the correct case. We did two cases, case 1 when p was non-integer, case 2 when p was an integer. So here in my case p is half, this is a non-integer, so I have to compare it with the solution of case 1, right? And that was of the form, but, or I should write it as comparing it with solution that was yx equal to, I should write yx here, and that was capital A jpx, capital B j of minus p x, right? So comparing with this, since where p was a non-integer, p does not belong to an integer, right? Okay, so on comparing these two, this jpx will be sin x by root x, right? We get jpx equal to constant times, there is always constant. Let me write that constant as alpha, right? Alpha is a constant, and 1 over root x sin x, right? And j minus p x is equal to beta, beta is my new constant, multiplied with cos x divided by root x, right? And yeah, choice of this alpha and beta. However, these are the solutions of this differential equation for the case when p equal to half, but in standard form these alpha and beta are chosen like root 2 by pi, right? Just like in Fourier, coefficient of Fourier series, the coefficient outside the integral was root 2 by pi. So same is the situation here. In standard notation we write jp. Why should I write j half here? Because I know that p equal to half, right? So I should write j half here, not p, j minus half, right? Okay, so j half x equal to, alpha is chosen like root 2 by pi, so root 2 by pi, and this x goes with this pi, right, times sin x, and j minus half x is equal to root 2 by pi x cos x. So these are standard Bessel's function for p equal to half and minus half, right? Okay, so yeah, we have found the particular values of j m plus half. Note that what we are doing, we are finding all the Bessel's function of this form j m plus half, and so far I have m equal to 0, because if I put m equal to 0 I will get this, if I put m equal to minus 1 I will get this, right? And in order to find the j 3 by 2, j minus 3 by 2, j 5 by 2, j minus 5 by 2, I have to use some recurrence relation. Using recurrence relation 6th, that was 2p by x jp x equal to j of p minus 1 x plus j of p plus 1 x, right? And if from here I obtain implies the values of j plus p1x, that will be of the type 2p by x jp x minus j of p minus 1 x, right? And yeah, and yeah, this is from here I will call it equation number 1, 2, or capital A, right? This is capital A, right? And if I put p equal to 0, no, not 0, then I will get 1. I should p equal to and multiple of 1 by 2, and if I put p equal to half, then I will obtain j3 by 2, right? If you want j half, I can use j half, yes. I can use j half minus half, yes, right? So using these two, I can obtain any value of j m plus half, right? So what I will do, I will put p equal to half, right? Then I will get j 3 by 2 x equal to, since p equal to half, this is 1 by x, and this will be converted to what? J half x minus j minus half x, and you can use these values. J half x is this much, so that will give you equal to 1 by root x, sorry, root 2 by pi, yeah, root 2 by pi x will be taken common, and from here you will be having 1 by x sin x minus cos x. This is the value of j 3 by 2, right? And similarly, if you put p equal to 3 by 2, right? Note that only fraction value of p is allowed, right? Especially multiple of half, odd multiple of half. So when this is this, okay, then putting 3 by 2 here, you will get j 5 by 2 x equal to, then it will become 3 by x, yes, 3 by x, j how much? 3 by 2, 3 by 2 x minus 3 by 2 minus 1, j half x equal to, we will take common, 2 by pi x will be taken common, and the value of, yeah, the value of what? J 3 by 2, that is this much, and that will appear here, root 2 by pi x. I think I have taken that value common already, yeah, that will be 1 by x sin x, but 3 by x is also there, so that will convert it into 3 by x square sin x minus 3 by x cos x. And what about the value of this thing? Minus j half, that is this much, and if I write minus cos x, yeah, minus cos x, minus cos x only, fine. So this is the value of j 5 by 2x, and similarly you can proceed j for j 7 by 2, j 9 by 2, and so on, right? But if I write this relationship again in that way, or try to obtain jp minus 1 in terms of this, then again from, let it be, I am calling it 1, from 1, this one, we can write as j of p minus 1 x can be obtained as 2p by x j px minus j of p plus 1 x, right? Now I want to obtain the j minus 3 by 2, negative suffix. So in order to obtain j minus 3 by 2, I should put p equal to minus half, yes, put p equal to minus half first. If you put p equal to minus half, you will get j minus 3 by 2 x equal to, here you put minus half, you will get minus 1 by x, j minus half, and j minus half will be used from there, and this will be j half, right? And using these values of j minus half and half from here, okay, root 2 by pi x will be taken out, and these both are negative signs, right? And this is j minus half, so that will be minus cos x by x, if I'm not wrong, right? And how appeared minus? Okay, putting value of p, fine. And then j half, that is minus sin x. This is the value of j minus 3 by 2. Similarly, we can obtain on putting minus 3 by 2, right? If I put j minus 3 by 2, it will give me j minus 5 by 2 x equal to minus 3 by 2. So that will be minus 3 by x j of minus 3 by 2 x minus 3 by 2 plus 1 j minus 1 by 2 x. And using these values, j minus 3 by 2 is this much. So what I will do, I will write this 2 by pi x inside square root outside, and inside bracket this minus 3x will be multiplied with this thing, so that you will get 3 by x square cos x and plus 3 by x sin x, and the value of j minus half from there is minus cos x. So this is j minus 5 by 2, and so on, right? You can continue this process infinitely. So from this method, first thing is that you are able to solve this Bessel's differential equation by one of the standard methods we studied in our last semester, and from there you can obtain the values of j m plus half, especially not any other value of the function. You cannot obtain j1x or j2x from this method. This method is applicable for the values of the Bessel's function, especially of the type jm plus half, right? And if you see these values, right, see the first value is containing sin x, cos x, sin cos, sin cos, sin cos, and sin cos are called elementary functions, right? You should know what are elementary functions. Elementary functions are sin x, cos x, e to the power x, the functions you are familiar with, right? Those are called elementary functions, right? And what are called special functions? Special functions are like Bessel function is a special function, Legendre's function, and that gamma function you studied in first semester, and Riemann's zeta function, right? So these are called special functions that are used extensively in mathematical physics and engineering, right? And elementary functions are like polynomials, rational function, right? Quotient function, sine, cos, exponential, they are in category of elementary functions. And you can see that all of these j's, right, jm plus half in general, are functions of elementary functions, right? And this happens only when this p is actually m plus half. For any other value of p, you will always obtain a big series, right? You have to write that in summation, and that will be obviously a special function. So if you want that you get this j in terms of elementary function, this p should be strictly of this nature, m plus half, otherwise you will get a special function, a series, right? So this is it for Bessel's function and its generating function. This is the end of the whole unit, the series solution, and in the next video we'll be looking forward, right? Thanks.